So the next subject we want to talk about is the function of a lens. Okay, so why we talk about the function of a lens? Because we say in Fraunhofer diffraction pattern, if you want to observe it, you need to stay at a position pretty far away from your aperture. That's how you can observe this Fraunhofer diffraction pattern. And the distance often is too large and too long, and it becomes unpractical for you to use it in real situation. So that's why we need to introduce a lens. Okay, the function of the lens, which is already put here, kind of a summary of the whole topic here. The lens, the purpose, the function of the lens will allow you to observe the Fraunhofer diffraction pattern at its focal plane. So let's go through it. So before we go through the function of a lens, let's review our spherical wave. So spherical wave, you can express it in this way. You have amplitude and you have decaying intensity when you propagate out, and you can express it as IKR minus omega t. Omega is the frequency, K is the wave number, R is the distance, right? And you can extract this I omega t term out. Okay, let's focus on this IKR term, and you can replace the R using this Cartesian coordinate S, Y, and Z, and you can again doing a binomial approximation, which is or you can say it partial or small angle approximation, so that you can use this parabolic form equation to calculate a spherical function. Okay, so that's how you get. Okay, that's what you get. So you can have extra IKZ term, and the other way is quadratic phase term here. And remember, look at this form. Okay, so when you have a positive sign here, you kind of having a divergent spherical wave. So let's look at the lens function of the lens here, and we all know that when you have a plane wave that illuminate in the lens, okay, and the lens has different thickness at different location. So the function of lens is that when you have a parallel light ray coming, they all get focused into its focal point, right? They all get focused into a focal point. And if you trace is the curvature of this wavefront, what you're going to see is that this is kind of this wavefront is kind of having this quadratic phase expression like here. Okay, compared to the previous spherical wave that is diverging out, this is kind of a spherical wave kind of converging to this focal point. Okay, so we can say the function of the lens is kind of introducing this kind of extra quadratic phase term to whatever wave coming here. If you have a plane wave, okay, you have uniform intensity everywhere, you have the same phase everywhere, but after this lens, at different location on S and Y or theta and eta, then you have different kind of phase delay here. So you can use this expression, which is before this is the amplitude before the field distribution before the lens, and after the lens you use a UL, the L is lens, U prime to represent this the amplitude function. Okay, so the after lens is equivalent to the image you have before the lens and times the transmission function, which is the function of the lens. And what this transmission function do is actually introduce extra phase term, a quadratic phase term to this input function. So your output function is like this. Output. So if you have unit amplitude plane wave coming in, and then the output function here is simply the transmission function of the lens itself. Okay, and so look at this. This is kind of a this kind of phase function is describing a wave, spherical wave that's converging to its focal point with a focal length f here. You can check it, check whether this phase function is correct or not by instead of converging a plane wave, you can see whether you can correct your spherical wave. Okay, so we say you have a spherical wave. Spherical wave has the phase amplitude. Let's see, the input phase amplitude should be j k to f eta, and so this is the input. Okay, and then when you pass through this quadratic phase term of the length, you're introducing an extra quadratic phase term. Okay, and these two terms when they come together become one. Okay, so you have spherical wave, and let's say you have a small angle here. Spherical wave coming into this lens, and then within a small angle, you can correct it into plane wave, which is equal to 1. Okay, this kind of show. Okay, this is the right expression of this transmission function of a lens. Okay, and let's see. So this is what we care. Okay, we want to check if what we just described is correct or not. Okay, so this is my input. I put the lens. I put the image input plane right in front of my lens, or pretty much touching. Okay, and assuming that I have a thin lens. Okay, thin lens means the thickness of the lens can be neglected. It's very thin. Okay, so you put your image plane, object plane, right in front of this, or touching, almost touching this, the front surface of this lens. Okay, so let's say you have input has this function ATA. This is aperture function. Okay, aperture function. Then here we will introduce some kind of aperture function here. Okay, why do we need to have this aperture function here? Because our optical system have limited size. Okay, and your lens has limited size. Okay, your lens has limited size, so you won't be able to, having a wave that's covering a very large area and then get focus. The maximum is, depend on the diameter of the lens. That will determine your aperture range too. So you need to have that kind of function there. The aperture function is simple, which is every light ray that is within this aperture, you can assume it is 100% transmitted. And every light ray that is outside this aperture, it becomes 0. Okay, so you also call it the pupil function, because every lens has a finite size. So in this case, this is your output. Your output equivalent to your input, which is these two times together. So this is your image function. This is the object amplitude, and you times it with the pupil function. Okay, so this will be the function you have in front of your lens. Now, the lens will introduce an extra quadratic phase term. Okay, so this is your function you have right after this lens. Okay, right after this lens. So that's your the function after the lens. Okay, so now from here to here, okay, from here to here, we know that you can use we want to calculate is Fraunhofer diffraction pattern. Okay, Fraunhofer diffraction pattern. Let's see what's a Fraunhofer diffraction, and because we know that Fraunhofer, sorry, it should be Fresnel diffraction pattern, because we know that Fresnel diffraction pattern can actually be accurate to quite close to your aperture, right? So from here to here, you can assume, okay, you can use Fresnel integral to calculate the image, how the light image change between these two planes. So okay, so let's see how it looks like. Okay, let's see how it looks like. So this is the Fresnel diffraction integral. Okay, this is Fresnel integration integral. You see, we still keep this the quadratic phase term here. Okay, we haven't canceled it out yet. Okay, that's why it's still a Fresnel diffraction pattern. If this term is canceled out, I mean, this become what? It becomes Fraunhofer diffraction pattern, right? So we want to see that. Okay, so now after this is the image pattern right after the lens. Okay, it's already multiplying these the lens transmission function. Okay, so what we do is that we just plug in what we have in the previous slide. Okay, so what's your UL prime here? Okay, what's your UL prime here? UL prime is the original function with the pupil and this extra phase term. Okay, pay attention to this extra phase term. Okay, this phase term is negative sign here, and here if you plug in this UL prime with the previous function, and that negative sign of the phase term will cancel out this term. So your Fresnel diffraction integral now become like this. So it's the input function and its Fourier transform. So what's this? This is exactly Fraunhofer diffraction pattern. So now you know what's the function of a lens. The function of a lens is to introduce an extra quadratic phase term so that you can cancel out this term. So instead of going to a distance pretty far away, in the previous case, the z need to be a lot larger than this so that this term can be canceled. Now you don't have to. When you put a lens here, and that just automatically cancel out. And what you have is that, look, this is f, okay? So this is f. Why is f? Because this represents the propagation distance. And here is the propagation from this right after the lens to the focal plane, okay? This f is your propagation distance in your Fresnel diffraction pattern. Now, okay, this is f, okay, this is f. So what this means is that at the focal plane, the pattern you're going to see is the Fourier transform of the image in front of your lens. Okay, so whatever image you put in front of the lens, its Fraunhofer diffraction pattern will be shown here. You don't have to go a distance pretty far away. You can see the Fraunhofer diffraction pattern at its focal plane, which is quite nice, right? How long is your optical focal length? It depends on what kind of lens you have. It can, if you regular convex lens, you can have 5 centimeter, right, 1 centimeter, or even if you have objective lens, it could be a couple hundred micron. Okay, so this is pretty nice. You don't have to go pretty far away. You can actually see the Fraunhofer diffraction pattern in its focal plane. Now, what is the Fraunhofer diffraction pattern? Is simply the Fourier transform of the image you have here. So it's kind of saying that between these two planes, this plane at the focal plane, you are seeing the Fourier transform of this input plane. Okay, of this input plane. So this is what you're going to have. Okay, so now everything you use to analyze the Fraunhofer diffraction pattern that we just told you on Monday or in the previous hour, you can pretty much use exactly the same thing, and you see the same pattern on its focal plane, except the z become f now, which is because you observe it in this focal plane. Okay, so which is quite nice, quite nice. Okay, so before, without the lens, if you have a circular aperture here, plane wave coming in, you need to see the Fraunhofer diffraction pattern, which is the square of its Fourier transform, pretty far away. But now you can see this Fraunhofer diffraction pattern at its focal plane. Okay, at its focal plane, and so what you need to do if you want to know what kind of pattern you're going to see in the focal plane, what you do is, okay, whatever pattern you have here, you take the Fourier transform of that plane, and then you will know what you're going to see in this focal plane. Okay, in its focal plane. Now, I want to talk about this ring here. Let's say, assuming you don't have any aperture at all, and this point should supposed to be just a point, right? Just a point. But now, since you introduce a limited size of aperture, so what you see here is the Fourier transform of that spherical, of that circular aperture. Okay, of that circular aperture. Okay, let me see if I have the pattern here. Oh, too bad, I don't have that pattern shown. Okay, but don't worry. I mean, in the next lecture, you will know, okay, what's the Fourier transform of the spherical of the circular pattern. Okay, so you will have this pattern. They call it airy disk. Okay, airy disk from the center to the first minimum. You will have a length scale equivalent to 1.22 lambda f over d. Okay, so if the aperture is small, spot size will be big. So compare of these two. Okay, so one is with a 0.5 millimeter hole here. So you have this size of this kind of airy disk pattern and diffraction pattern of the spherical aperture. And if that diameter is big, actually you can have a smaller size of this disk here. Okay, so this is the this actually determines what is the minimum spot size you can detect. What's minimum spot size you can detect in the optical system. Okay, what determined that? Is the two things. One is the focal length. The other one is your aperture. Okay, it's your aperture. Okay, so ratio of these two is what? It's some kind of similar to this is length diameter. Okay, so some kind of similar to the numerical aperture number, right? So we say the higher the numerical aperture, that means that the larger the aperture and shorter the focal length, that's what give you the very high numerical aperture. Okay, so that means this is large, this is short, which means that this spot size will be small. That's why high NA optics can give you a smaller spot size. Okay, and you can precisely describe, calculate it using just simply finding out what's the Fourier transform of your spherical aperture size. Okay, spherical aperture size, and you know what kind of minimum spot size you can have. Okay, so when you want to determine, okay, what is the optical diffraction limit, this airy disk is can help you determine it's a limit. Okay, you won't be able to get a size that's smaller than the airy disk. Okay, airy disk. Now, if you want to know, whether you can resolve two spot, very high, small spot that are positioned very closely together. You want to know how close you can put them and still resolve it. So the size of the area disk is very good. It's a very good way that can help you to determine that. Okay, so let's say you have a two point source. Okay, and then each one of them form an area disk. Okay, so if the area disk formed by 2 point source is far away enough, you can still have these two peaks that can be detected. When they get close enough, once simply a little bit overlap, you still can have the two peak pattern, right? This one move to this one, okay, so then you have only one single peak. Okay, this is the point that you can just resolve this and know that there are two spots here. Now, if they get even closer, then this is what you're going to have. You won't be able to tell, hey, there's actually two spots separated by some certain distance if they get too close enough. Okay, if they get too close, you won't be able to resolve them. Okay, so this kind of this is the rule. It's called Rayleigh criterion, and that is saying that when the center of two very small dots separated, when this area disk pattern overlap, when separation distance equivalent to the area disk pattern, then you won't be able to resolve this two spot. Okay, you won't be able to resolve this two spot. So that's this is where the optical diffraction limit comes from. It comes from your limited size and comes from your limited lambda, and because you are using some certain light of, so it comes from your numerical aperture. Okay, it's come from light source, come from numerical aperture of your optical imaging system or projection system. Next is a topic that we won't include it in the final exam, but I think it's worth mentioning here in case that some of you may be interested to go further to do optical imaging and also being able to handle this phase propagation term. Okay, we just say that in case one, what we do is that we put the object plane right in front of this lens, and we are able to detect the Fraunhofer diffraction pattern in the focal plane. Okay, these two are pretty much just the Fourier transform. Okay, amplitude is simply just Fourier transform. In some cases, that there may be a need that for you to still keep this the phase term, and not simply just ignore them. Okay, in that case, what I'm going to show you is that if you're able to put this object image in the front focal plane, okay, in the front focal plane, because the free space propagation, you can decompose this into different kind of plane wave, right? And different kind of plane wave, when they propagate in the free space, they will introduce some quadratic phase term, and that quadratic phase term will allow you to cancel these two. Okay, and the lens before and after will allow you to cancel this term. So in that case, if you put the object in the front focal plane, and what you detect in the back focal plane is exactly the Fourier transform. Okay, exactly the Fourier transform. This is a common phase term. A lot of times you can just ignore it. So it's exactly the Fourier transform with this amplitude that may be slightly they modulate by this lambda and f here, okay? But what's inside is exactly Fourier transform, and you don't even have that kind of extra phase term here, okay? You don't even have that kind of extra phase term here. So then, which is just to let you know, and a lot of so this is one example, okay? This is one example, which is the very famous 4F optics imaging system, okay? It pretty much can explain this result pretty well, okay? So what you have here is that you have object and you position in the front focal plane of the first lens. You use plane wave with uniform intensity to shine to this object. After that, okay, you have this field distribute pattern equal to the F character here, and then that you will be able to detect the Fourier transform of this aperture pattern, and this is the Fourier component of this aperture pattern, okay? And then let's say you put another lens here, okay, and this Fourier plane or the focal plane of the first lens is positioned at the front focal plane of the second lens. You know, you are doing kind of another Fourier transform, okay? So you're doing two Fourier transform. And remember that when we do Fourier transform, okay, an inverse Fourier transform, you have one is times exponential ij 2 pi f x, right? And the other one is simply just there's no minus sign there, okay? So inverse with a minus sign, and no, Fourier transform with a you times it with exponential with the phase term has a minus sign there. But inverse Fourier transform, you don't have that kind of minus sign, okay? But here is like, but there looks very close, right? It looks very close. It's simply by that minus sign. So here is that if you do two Fourier transform, you know, it's kind of, you know, you just having that kind of two minus sign effect, okay? So you do, you're supposed, if you want to do reverse to construct this image, you're supposed to have an inverse Fourier transform, but instead you are doing another Fourier transform, okay? So that's the optical image you will get, okay? It looks very similar. Now, if every frequency component and decompose, and all these frequency components can be again well preserved and propagate to this plane, when you synthesize the image back again, you will be able to reproduce exactly the same pattern at these two sides, right? Now, in many optical systems, a lot of time we may have a need to kind of to take out some of the frequency component in this image, okay, for different kind of application. Some would be trying to take away the center part. So what you're going to do is that you put a aperture stop in the middle, okay, you take out the low frequency component and only add the high frequency component to pass through, and you form construction here. Or you can simply just maybe you want to remove any higher order term here, okay? So you can use just a kind of pinhole to allow some sort of frequency to pass through, okay? So if, for example, in this one, if you have some kind of aperture position in the Fourier plane, okay? So it's kind of an approach allow you to select, okay, which frequency to pass, which frequency not to pass, okay? Like in this case, you have a limited size of the ring, which is a high frequency component will be blocked, okay? So the high frequency component is blocked, then when you synthesize the wave again, you won't see the very detailed fine features, okay, because the high frequency component is gone, right? So this is just, we won't test you in the final exam, but I think it would be good for you to know what's the, this kind of 4F optics and what happened when you position the object in the front focal plane of a lens. Okay, so you can create so in the front focal plane and the back focal plane of the lens, you can do an exact Fourier transform. Okay, you don't have to worry about the phase turn, which is really nice. Okay, and that's it.